Next is aromatic hydrocarbons. See, the aromatic hydrocarbons also called arenes. See, the most of them are possess a pleasant odor. So the pleasant smell. So the class of compound was named as aroma. That is, aroma means smell. So that is why they are called aromatic compound. See, the most of the compounds contains benzene ring. The benzene ring is a highly unsaturated compound. But in a majority of the reaction, the aromatic compounds, the unsaturation of benzene ring is retained. However, there are examples of aromatic hydrocarbon which do not contain a benzene ring, but instead contain other highly unsaturated rings. So the aromatic compounds containing benzene rings are called benzenoid compounds, and not containing a benzene rings are called non-benzenoid compounds. So these are the aromatic hydrocarbons. So the benzene, toluene, naphthalene, biphenyl. Then nomenclature and isomerism. See, the nomenclatures of aromatic hydrocarbon is already we discussed. That is in last lesson, some basic concepts of organic chemistry already we seen. See, all the 6 hydrogen atoms in the benzene ring, look at this, are equivalent. So it forms only one type of the mono substituted product. When 2 hydrogen atoms in a benzene rings are placed to 2 similar or different monovalent atoms are grouped, 3 different position isomers are possible. That is, one is, see, suppose this is a group means the adjacent position. So these are called in commonly they are called ortho position. The next to adjacent position is called ortho. This the next adjacent to the next position is, and the opposite side this is called meta position, and or simply we can tell that is 1 2, that is R 1 6. This is 1 2 or 1 6 is ortho. Then 1 3 1 3 and 1 5, simply 1 5 are called meta. We can write it like this: 1 2 3 4 5 6. So 1 2 and 1 6 simply called ortho, 1 3 and 1 5 simply called meta, and the opposite, that is 1 4, is called para position. See, this is the derivatives of benzenes. The first one is, this is methyl benzene, the commonly called toluene. This IUPAC name is methyl benzene. Suppose 2 methyl groups are present in this position, means suppose the 1,2 dimethyl benzene for this IUPAC name. The common name is, the well-known compound is common name. So ortho position is methyl group is present. So that orthoxylene. Look at this compound 1 3. 1 3 means I already said meta position. So that the metaxylene. Then IUPAC name is 1 3 dimethyl benzene. Similar way, in the position of para, the methyl group present in the para position means there is 1 4 dimethyl benzene. The common name is paraxylene. Okay. Then structure of benzene we'll see. The structure of benzene like that. The molecular formula is C6H6. So it indicates the high degree of the unsaturation. So the molecular formula did not account for its the relationship to the corresponding alkanes, alkenes and alkynes, which you have studied in the earlier section of this unit. Okay. So suppose that unique property and the unusual stability, they have that where is assigned its structure. So benzene was found to be a stable molecule and found from a triozonide, which indicates the presence of the 3 double bonds here, the 3 double bonds of benzene. So benzene was further found to produce one and only one monosubstituted derivative, which is indicated that all the 6 carbon and the 6 hydrogen atoms of the benzenes are identical. Look at this. On the basis of this, see Kekule's rule, that is the Kekule's structure observation, who is scientist of the benzene isolated person, Kekule. The name is So Kekulé. So this is a Kekulé structure. See, this benzene having the cyclic arrangement of 6 carbon atom with the alternate single and double bonds and one hydrogen atom attached to each carbon atom. Look at this, alternated double bond and each carbon atom attached with hydrogen atom. So this is called Kekulé structure. So the Kekulé structure is indicate the possibility of the two isomeric, that is the 1,2 dibromobenzene. Suppose if I write here and here, this is 1, dibromobenzene. So if one of the isomer, the bromine atoms are attached to the doubly bonded carbon atoms, whereas in other they are attached to the singly bonded carbon atom. So this is the possible one. Then, however, the benzene was to form only the one ortho substituted problem. This problem was overcome by Kekulé by suggesting the concept of the oxalating nature of double bond in the benzene ring. See, like this. Suppose the benzene structure you can write like this, or you can write like this. So that you can write this is also benzene and this is also benzene, or you can write it simply put a circle in the benzene ring. That is this is also called benzene, one of the other structure. Okay. Next is the resonance and the stability of the benzene. See, according to the valence bond theory, the concept of oxalating double bonds with benzene now will be explained with the resonant hybrid. See, benzene is the hybrid of various resonating structure. The two structure of, that is A and the B, is given by the Kekulé. So the main contributing structure, so that the hybrid structure is represented by interesting a circle or dotted like this. The dotted circle in hexagon is also called the benzene structure. See, the circle represents the 6 electrons which are delocalized between the 6 carbon atom in the benzene ring. Okay. Then the orbital overlapping gives a better picture about the structure of benzene. All 6 carbon atoms. See, the all 6 carbon atoms having benzenes are sp2 hybridized and 2 sp2 hybrid orbitals of each carbon atom overlap with the sp2 hybrid orbitals of the adjacent carbon atoms to the form 6 carbon-carbon sigma bond, which are in the hexagonal plane. So the remaining sp2 hybrid orbitals of each carbon atom overlap with the s orbitals of the hydrogen atom to form 6 carbon hydrogen bond. So this is the carbon hydrogen bond, like 6 carbon hydrogen bond. That is also sigma bond. So each carbon atom is now left with one unhybridized p orbital perpendicular to the plane of the ring is like this. So the unhybrid p orbitals of carbon are close enough to form a pi bond by lateral overlapping like this. This is the lateral overlapping of the pi bond. So there are two equal possibilities of forming pi bonds by overlaps of p orbitals. See, look at this C1, C2. Another one is C3, C4. That is C3, C4, and C5, C6. This one possibility, or you can write it like this. And the next possibility is C2. Then this is right here 1, 2, 3, 4, 5, 6. C2, C3, or then C4, C5, then C1, C6. So the R C6, C1. So these are the possible arrangement. This is the structure. Okay. So the structures like the corresponding Kekulé structure with the localized pi bond. These internuclear distance between the all carbon atom the ring has been determined by the X-ray diffraction to be the same. So there is a equal probability for the p orbitals of each carbon atom to overlap with the p orbitals of the adjacent carbon atom. Okay. And then next is the aromaticity. Benzene was considered as parent aromatic compound. Now the name is applied to all ring system, whether are not having the benzene ring. So they have possess the following characters, like first planarity, complete delocalization of pi electron in the ring. Third is presence of pi electron in the following ring, that is n is equal to integer. It can be 0, 1, 2, 3, whatever it is. So this is a 4n plus 2 rule. That is the also called, it's often referred to as Heckel's rule. See, these are the some examples of compounds are the aromatic compounds. See, this is benzene and this is cyclopentadienyl anion. This is cycloheptatrienyl cation. Positive charge present, so that cation. See the benzene, here the n is equal to 1, so that this having 6 electron. For example, n is equal to 1 means what? That is the rule is 4n plus 2. So here 4 into 1 plus 2, it will become 6. So that 6 pi electron. So 6 pi electrons mean each this 1 pi electron, this having 2. So this bond having 2 and this bond having 2. So that 6 electrons are, the 6 pi electrons are present. In this compound, this is benzene, this is for cyclopentadienyl anion. This is cycloheptatrienyl cation, because 7 rings, 7 carbon atoms are present. 1, 2, 3, 4, 5, 6, 7. Okay, then 3 bonds are present inside the ring, so that n is equal to 1, so that 6 pi electrons are present. For this compound, look at this. Here n is equal to 2 means apply the rules in this formula, you will get 10 pi electrons. So 1, 2, 3, 4, 5. So 5 into 2, 10. So 10 pi electron. This is compound is called naphthalene. And when n is equal to 3, when n is equal to 3 means there is anthracene and phenanthrene. So this having the n is equal to 3, that means the 14 pi electrons are present. 1, 2, 3, 4, 5, 6, 7. Similarly here 1, 2, 3, 4, 5, 6, 7. Okay. So these are the example. Next, preparation of benzene. Already we seen the cyclic polymerization of ethene. Yes, that is ethine. Already we seen. Next method, that is the decarboxylation of the aromatic acid. You will get the benzene compound. Then the reduction of phenol also, you will get the benzene. See, this is the preparation method. The sodium salt of benzene reactive with the sodium hydroxide in the presence of calcium oxide on heating, you will get benzene. Then the reduction of phenol from in the presence of zinc metal on heating, you will get benzene and zinc oxide. So this is the basic preparation method for benzene. Then the physical and the chemical properties of benzene. The physical properties, the aromatic hydrocarbons are usually non-polar in nature. Usually they are colorless liquid or solid with a characteristic smell. And already you are familiar with the naphthalene balls, which is used in the toilets and for preservation of the clothes because of the unique smell of the compound and the most repellent property. So the aromatic hydrocarbons are immiscible with water but are readily miscible with organic solvent. Then they burn with sooty flame also. Then the electrophilic substitution reaction. The first reaction is that is commonly the electrophilic substitution reactions are arene or nitration, halogenation, sulfonation, Friedel-Crafts alkylation, and the acetylation reaction which attacking reagents are called electrophile. First we will see the nitration reaction. The nitration reaction, when benzene treatment with the concentrated nitric acid and the concentrated sulfuric acid, it will give the nitro, benzene and water. So this process name is called nitration. Then this is the halogenation. So using of halogen. So arenes react with halogen in the presence of the Lewis acid, like anhydrous, aluminum chloride or ferric chloride or ferribromide or whatever it is, you will get the haloarenes. So this is the haloarene. So if you use the chlorine react with the benzene in the presence of anhydrous AlCl3, you will get chlorobenzene and HCl. Okay. Next is sulfonation. So this is the sulfonation reaction, when the replacement of the hydrogen atom by the sulfonic acid group in the ring is called the sulfonation. It is carried out by heating benzene with the fuming. This is the fuming sulfuric acid, that is also called oleum. Okay, H2S2O7. The formula simply we called H2S2O7. that is fuming sulfuric acid. See, you will get the sulfonic acid, that is benzene sulfonic acid. Then this is the Friedel-Crafts alkylation reaction. Simply we called Friedel-Crafts alkylation reaction. When benzene treatment with an alkyl halide in the presence of anhydrous aluminum chloride, the alkyl benzene is formed. So the alkyl benzene, that is the methyl benzene, is formed. When treatment with the ethyl chloride, you will an anhydrous aluminum chloride, you will get the ethyl benzene. So this is the Friedel-Crafts alkylation reaction. Okay. Then the Friedel-Crafts. This is the next is Friedel-Crafts acylation reaction. So the reaction of benzene with the acyl halide. This is the acyl halide. That is the acetic acetyl chloride. In the presence of the Lewis acid like aluminum chloride, on heating you will get the acyl benzene. Okay, that is also called toluenes. See, this is not COCH3, this is a CH3. So this is toluene I will get. Sorry, it's correct one. COCH3. So that is the acetophenone. And treatment with the acetic anhydride in the presence of aluminum trichloride, aluminum chloride, simply on heating you will get the acetophenone and the acetic acid. Then if excess of the electrophilic reagent is used, that is the further substitution reaction may take place in which other hydrogen atoms of the benzene may also be successively replaced by the electrophile. For example, benzene on treatment with the excess of the chlorine, this is chlorine is excess, in the presence of the anhydrous aluminum chloride, on heat on dark condition, cold condition, you will get the hexachlorobenzene, that is C6Cl6, and HCl is obtained. So this is the reaction. Now mechanism of the electrophilic substitution reaction we'll see. See, the mechanism of electrophilic substitution reaction, the main the three steps are following here. The experimental evidences, that is the substitution and the electrophilic reactions are the supposed to proceed via following three steps, that is generation of electrophile, then the formation of carbocation of the carbocation intermediate, then the removal of the proton from the carbocation intermediate. So these three steps are we are usually following. So first, generation of the electrophile. The generation during the chlorination, the alkylation and acetylation of the benzene, anhydrous aluminum chloride being a Lewis acid, so helps to generation of the electrophile, that is Cl plus, simply we can write it like this, Cl plus R plus Rc plus O, that is acylinium ion, the combining with the attacking reagents like this. See, the Cl bond is created, that is the attacking reagent like this to form a chloronium ion. Then when react with methyl chloride to form methyl cation, then acetyl chloride, this will be formed, that is another one, that is CH3 C double bond O, that is the carbonyl cation, methyl carbonyl cation is formed. So that here in the case of the nitration, the electrophilic nitronium ion NO2 plus is produced by the transfer of proton to the nitric acid. See, this is the following manner. Suppose that H2SO4 using the sulfuric acid in the presence of the nitric acid and what happens when this lone pair of electron to attack this and this shifted here like this. So you will get like this, H positive charge is created on the oxygen atom, then you will get the hydrogen sulfate. The step 2, again that nitration, that is the protonated nitric acid. This is called the protonated nitric acid. This is the protonated nitric acid. So again the positive charges are stabilized by this and form the nitronium ion. So it is interesting to note that the process of the generation of nitronium ion, the sulfuric acid serves as an acid and nitric acid as a base. So the simple acid base equilibrium, this is we call simply acid base equilibrium. The next step is the formation of the carbocation or arenium ion. See, the formation of carbocation, that is the arenium ion, the attacking of electrophile results in the formation of the sigma complex. That is sigma complex or the arenaceous ion, which the one of the carbon is sp3 hybridized carbon. So this is the sigma complex arenaceous ion. So the arenaceous ion gets stabilized by the resonance like this. So this is the resonance stabilized structure of the arenaceous ion. Then see, the sigma complex or the arenaceous ion is loses its aromatic character because the delocalization of the electron stops at the sp3 hybridized carbon. Then the next step is the removal of the proton. So removal of proton is to restore the aromatic character. Sigma complex release the proton from sp3 hybridized carbon ion attacked by AlCl4 minus. That is in case of the halogenation, alkylation, and the acylation, and that HSO4 in case of the nitration. Okay, well, this is the reason. Then the addition reaction. See, the addition reaction, the addition reaction under vigorous condition, that is the high temperature or and high pressure in the presence of the nickel catalyst, the hydrogenation of benzene gives the cyclohexane. Then under the ultraviolet light, 3 chlorine molecules add to benzene to produce the benzene hexachloride, that is C6H6Cl6, which is also called gammaoxane. Okay. Then the combustion reaction. The combustion reaction, when heated with the air, benzene burns with sooty flame to producing the carbon dioxide and the water. So the general combustion reaction for any hydrocarbons can be write like this. This is the chemical equation. Then the directive influence of the functional group, the monosubstituted benzene. That is, that when the monosubstituted benzene is subjected to further substitution, 3 possible distributed products are not formed in the equal amounts. That is, the 2 types of behavior are observed. That is, either ortho and para products or the meta products is predominantly formed. So it is also the nature of the substituent already present in the benzene ring and not on the nature of the entering the group. That is the known as the directive influence of the substitution. The reason for ortho or para or meta directive nature groups are like this. First we will discuss the ortho and para directing group. Suppose the portion of the ortho portion, the phenol, the group which direct incoming group to the ortho and para portions are called ortho para directing group. See the influence of that phenolic group, that is the phenol resonance hybrid having the 5 structures. The structure, look at this, the phenolic, the lone pair of electron is attached here. What happened? This bond is shifted here, so you will get the oxygen having created the positive charge, then this bond is shifted here, and then the delocalization of electrons one by one, you will get the 5 resonating structures. So it is clear from the above resonating structure that the electron density is more on the ortho and the para portion. Look at this, this is ortho and this para portion. The meta portion is this. Okay, this is the meta portion. There is no delocalization on the meta position, only in the ortho and the para direction. So that is, however, it may be noted that the minus A effect of the OH groups also operates, due to which the electron density on ortho and para position of the benzene ring is slightly reduced. So, but the overall electron density increases at the position of the ring due to the resonance before the OH group activates the benzene ring for the attack by the electrophile. Then other example, NH2, NH2R, amide, alkoxy group, methyl group, ethyl group, like this. Okay, then in case of the aryl halide, the halogens are moderately deactivating because of their strong minus A effect. This is the main reason. The overall electron density on the benzene ring decreases it, and it makes the further substitution is very difficult. So, however, due to the resonance, the electron density on ortho and para position is greater than that of the meta position, so that they are also ortho and para directing group. Now we will see the meta directing group. See, this is the meta directing group for the resonating hybrid structure, resonance hybrid structure. The group which direct the incoming group to the meta positions are called meta directing groups. Example, the meta directing groups, we can write it, I will write here, that is NO2 group, then the CN group, that aldehyde group, then COR group, then carboxylic acid group, ester group, sulfonic acid group. So like this. So now we'll take the example of the nitro group. The nitro group reduce the electron density in the benzene ring due to this strong minus I effect in the nitrobenzene. Resonance hybrid is like this. See, the NO2 I'm going to write like this. What happens means first the bond is splitted, this shifted here, and what happens, this double bond gets broken, then create a negative charge in this carbon in this oxygen atom. So what happened, positive charges are created in this ortho position. So then ortho position again on stabilize the positive charge, this electron is shifted here, and what happened, positive charge is created here. Then the third position again the positive charge is stabilized to this structure. So what happens, this this bond is shifted here, so the positive charge is created here. Then again the regaining, that is the re-stabilizing the resonance hybrid. So they have the 5 resonating hybrid structure. So in the case of the overall electron density on the benzene ring decreases, making further substitution is difficult. Therefore these groups also called the deactivating group. So the electron density on ortho and para position is the comparatively less than the at meta position. So the electrophilic attacks on the comparatively electron rich meta position, resulting in meta substitution products. Then the carcinogenicity and the toxicity. The benzene benzene in the polynuclear hydrocarbons containing more than 2 benzene rings fused together are toxic and set the process that is called cancer producing property, that is the carcinogenic. Such as polynuclear hydrocarbons are formed on incomplete combustion of the organic materials like tobacco, coal and petroleum. So they enter into the human body and undergoes a various biochemical reaction and finally damage the DNA system and cause cancer. So, okay, that some carcinogenic chemicals like 1,2 benzanthracene, then that 3-methyl chloroanthracene. So see, these are the examples of the carcinogenic chemicals. Okay, thank you students.